Okay, so this is question number 3 in workshop number 12. This question is related to the topic we learned in lecture 11 with elasticity, stress, and strain. So it says here in last week's lecture on torques and equilibrium, we saw that for a diver standing on the balls of his feet, the tibia bone exerts a force of 1,750 newtons on the ankle. So that's the yellow arrow in the diagram below. So this yellow arrow here is the force exerted on yes exerted on the ankle by the tibia. And then the diver's tibia is 36 centimeters long and can be approximated by a hollow cylinder of outer radius 12.0 millimeters and inner radius 6.0 millimeters. The question is the tibia in tension or compression? Okay, so to answer that, notice that this yellow arrow is the force exerted on the ankle by the tibia. We cannot use this yellow arrow because what we want to find is whether the tibia is in tension or compression. And the yellow arrow is exerted on the ankle, not on the tibia. But we know from Newton's third law of motion that if the tibia exerts a force on the ankle, then the ankle should also exert a force on the tibia. So if we um, illustrate that here, the reaction force will be opposite in direction. And then we can say that this here is the force exerted on the tibia by the ankle. Right? And the amount of force exerted on the tibia will be the same as the amount of force exerted on the ankle, which is given to be 1,750 newtons. So the amount of force is equal to 1,750 newtons. The amount of force on the tibia is equal to the amount of the force on the ankle. Yeah, so if you notice here, this is the tibia bone. Yeah. So this whole bit, just change colors for that to make it easier to see. Yeah. So the tibia bone is this thing. So this is the tibia. And the force that's being exerted on the tibia is this upward force. So you can see here that it's a compressive force, right? It's parallel to a perpendicular, sorry, it's perpendicular to the cross-sectional area of the tibia, and it's pointing inwards towards the tibia. Therefore, the tibia is in compression. In compression. Okay, so the next question asks us to calculate the stress in the tibia, and then the strain in the tibia, and the change in length of the tibia. And we're given here the Young's modulus for the tibia bone is 10 times 10 to the 9 pascals. Okay, so let's write down what we know, what we're given. So we're given the length of the tibia is 36 centimeters. We convert this to meters by dividing by 100. Then we have 0.36 meters for the length. The Young's modulus is given to be 10 times 10 to the 9 pascals. And then the inner and outer radii. So the outer radius is equal to 12.0 millimeters. If we convert this to meters, we divide by 1,000. So yeah, or we also know that milli, the prefix milli means times 10 to the minus 3. Okay, that's the prefix milli here. Times 10 to the minus 3. Okay, and so if you expand out that scientific notation into a number, you'll have the inner radius in meters to be 0.012 meters. Okay, and for the inner radius of the bone is 6.0 millimeters. So again, we also convert that to meters. You can either divide by 1,000 or you expand out the prefix milli to times 10 to the minus 3 and express that as a number, and you get 0.006 meters being equivalent to 6 millimeters. Okay, so the fact that the bone has an inner and outer radii, we can, so I think it also says that it can be modeled as a hollow cylinder. And the cross-sectional area of a cylinder, so if you get a cylinder, cut it in half and look through one end of the cylinder, you'll see that the cross-sectional area of a cylinder is a circle. But it's a hollow cylinder, so you have here the cross section of the hollow cylinder. So you have, it's given there, the outer radius of this hollow cylinder, which models the bone, is so this is R outer, 0.012 meters, and the inner radius R inner is 0.006 meters. So inside of this is hollow. Yeah, maybe let me just do this. It's probably clearer. So this is hollow, and the bone is just this part. Okay. The solid part is the bone, and there you have a hollow inner core. Okay, so the first question we're being asked for the stress, we learned that stress is defined as force divided by area. Okay, the force, we already know that. Actually, the force on the tibia, is equal to 1,750 newtons. Okay, so that's what we figured out in our earlier discussion. Yeah, the tibia bone exerts a force of 1,750 newtons on the ankle, but Newton's third law of motion says that the ankle should also exert 1,750 newtons of force on the tibia. So the force on the tibia is known. So we can, looking at the equation for stress, we know the force. We then have to figure out what's the area of the bone. So find the area of the bone over which the force is being exerted. Right. So the bone is hollow, so that means you have to find the area of the solid bone, whose radius is 0.012 meters. Okay, so you can think of this, the bone of this outer radius as defining a solid bone. Okay, but then you have to take away or minus the area of the hollow part or hollow section of the bone with radius of 0.006 meters. Okay, so recall the area of a circle is equal to pi r squared. Okay, therefore the area of the bone, the area of the solid bone with radius 0.12 meters will be pi r outer squared, so the outer radius, and take away the area of the hollow core. So that will be pi r inner radius squared. Yeah. So it's the whole thing. So it's the first expression here, pi r outer squared. That's the area of the solid bone. If you consider that this whole cross-sectional area is solid and the radius is 0.012, that's the area of the solid bone. But then you have to take away the area of the hollow part, which is pi r squared, with r being the inner radius. Okay, so substituting numbers, you have pi times 0.012 squared. Don't forget the square. Minus pi times 0.006 squared. Don't forget there's a square there. Okay, so carry out the calculations. You have to do the square first and then multiply that with pi. You should get something like 4.52389 times 10 to the minus 4 for the solid bone, and 1.13097 times 10 to the minus 4 for the hollow part, giving you an area for the bone of 3.39 times 10 to the minus 4 meters squared. So that's the cross-sectional area of just the bone part, okay, taking away the hollow part of the bone. So then you can now solve for the stress is equal to the force, 1,750 newtons divided by the cross-sectional area, 3.39 times 10 to the minus 4, gives you a stress of 5.2 times 10 to the 6 pascals. Right. Okay, next question, question B, is to find the strain. Okay, so from definition, we know strain is the change in length or the deformation divided by the original length. But in this case, we don't know the change in length. We don't know delta L. We don't know the deformation. In fact, that's the next question that we need to solve. But we can use an alternative equation because we know the Young's modulus, it was given. And the Young's modulus relates the stress to the strain. So Young's modulus Y is equal to stress over strain. We already know the stress from the previous question. The Young's modulus is given, so all we have to do is rearrange this equation to isolate strain. So if I flip the equation, I have 1 over y on one side, and I have strain over stress on the other side. Okay, I multiply both sides with stress. Right, that gets rid of stress on the right hand side, and therefore I have the equation of strain is equal to stress divided by the Young's modulus. So just substituting the numbers now, 5.2 times 10 to the 6 for the stress, which we've solved earlier here, the stress, divided by the Young's modulus, 10 times 10 to the 9, gives us a strain of 5.2 times 10 to the minus 4. Remember, strain doesn't have a unit because the unit for stress cancels with the unit for Young's modulus. Okay. Right, so that's the strain, and we've solved for the stress earlier. Okay, and then the last question is to find delta L. So we can use now strain is equal to delta L over L0, multiplying both sides with L0 gives us the equation for the deformation. Delta L is equal to the strain times the original length L0. And we know both things. Strain, what we solved earlier, 5.2 times 10 to the minus 4 times the original length of the tibia, 0.36 meters. And that will give us a strain, a deformation or delta L of 1.9 times 10 to the minus 4 meters. All right. Okay, so that's the solution for question 3 of workshop 12. For the solutions of questions 1 and 2, we've solved that during the lecture, so just refer to the video of the lecture 12.